Good day and welcome, everyone. I'm Jack Van Horn from the University of Virginia. Please allow me to welcome you to this edition of our 2020-2021 Foundations of Biomedical Data Science Seminar Series. This lecture is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA Brain Institute, the College of Arts and Sciences, the School of Data Science, and through a grant from the National Institutes of General Medical Sciences. It is my honor and my privilege today to welcome our speaker, Dr. David Kennedy from the University of Massachusetts. Dr. Kennedy is a professor of psychiatry at the University of Massachusetts Medical School. He is the director of the Division of Neuroinformatics at the Child and Adolescent Neurodevelopmental Initiative called CANDI. He has extensive experience in the development of image analytic techniques and was a co-founder of the Center for Morphometric Analysis at Mass General Hospital. His career has seen the advent of such technologies as MR-based morphometric analysis in 1989, the arrival of functional MRI in 1991, and the development of diffusion tensor pathway analysis in 1998. He has a long-standing experience with the development of neuroinformatics resources and participation in the Morphometry Biomedical Informatics Research Network, or mBIRN. Dr. Kennedy is the community liaison for the Neuroimaging Informatics Tools and Resources Clearinghouse, called NITRC, a fantastic resource for all manner of software and executables that deal with neuroimaging related informatics. In addition, he is the founding editor of the Journal of Neuroinformatics that debuted in 2003, and a PI of ReproNim, the Center for Reproducible Neuroimaging Computation. Dr. Kennedy's lecture today is entitled ReproNim Towards Reproducible Neuroimaging Neuroscience. As always, we are streaming this lecture live and for recording via YouTube. If you are watching via YouTube, thank you so much for joining us today. Also, our specially selected 2020-2021 Biomedical Data Science Innovation Lab participants are encouraged to submit any questions for Dr. Kennedy by the chat feature in their Zoom sessions. I will synthesize these questions and ask them on your behalf during the last 10 minutes or so of the lecture. And with that, welcome, David. We are very much looking forward to your lecture.
Thank you so much, Jack. It's my pleasure to join you in this exquisite seminar series. And as you were mentioning, it's part of a long-standing education and outreach effort that, again, you've just been monumental in spearheading. So I appreciate the invitation. The introduction you provided, while nice, means only two things. One, I'm old. But two, when I was young, there were some really cool things going on. And so I was a very fortunate person to be in the right place at the right time during development of all of the sort of cool, MRI-based, neuroimaging methodologies. So that was an opportunity. So the key driving topic I'd like to talk about today is reproducibility. And again, it's motivated by our NIBIB funded center called ReproNim, Center for Reproducible Neuroimaging Computation. So reproducibility will be my main theme. And so I wanted to come up with, some sort of motivational types of things. Now, reproducibility is a problem in lots of different topics. We'll be specifically considering it in the context of neuroimaging, but all the concepts and all the issues really, are pan-disciplinary in terms of other fields and other approaches to brain and science in general that need to keep these kinds of concepts in the front of one's mind. But by focusing, I often come back to so my work tends to be in psychiatric applications, principally child psychiatric applications, development and misdevelopment, and autism and other behavioral and developmental disabilities. So since I work sort of on this psychiatric side of things, one of my go-to statements, which really motivates a lot of what I'll talk about and a lot of what the center is really working on, comes from a paper by Tom Insel and his colleagues. Tom Insel at the time was the head of the National Institutes of Mental Health, and he was sort of bemoaning, the lack of progress, in sort of mental health, in psychiatric, science, generally. And while I hate to read a long quote, I think I do want to read this one to make sure that a couple of points, come out. So patients with mental disorders show many biological abnormalities which distinguish them from normal volunteers. However, few of these have led to tests with clinical utility. So again, that's lamenting the fact that today, the clinical tests we have in psychiatric clinic are very similar to what they were 10, 20, 30 years ago, before a vast investment in neuroimaging, a vast investment in genetics, et cetera. So again, we have very little new clinical utility tests that have come out of this investment. Several reasons contribute to this delay. First, there's a lack of a biological gold standard definition of psychiatric illnesses. And again, this portrays the shift that the National Institutes of Mental Health had back around this time, from sort of diagnoses to research domains of classification. So again, a lot of the behaviors span diagnoses, and diagnoses tend to be spectrums and checklists and things like that. So not the best sort of marker for what is going on behaviorally, when it's a checklist that you're giving you that diagnosis. So that really launched this switch into trying to find systems and circuits and behaviors that go together, not a diagnosis that ends up being the end target. A profusion of statistically significant but minimally differentiating biological findings have emerged. And to this we really mean that over the past 25, 30 years, there's been tens of thousands of papers. People have done tens of thousands of studies, have found things, so lots of things get found, but these ultimately are significant, but not informative in terms of outcomes and treatments and types of things to do. And this is confounded by the fact that there are only approximate replications of these findings, and that's often done in ways that neither confirm nor refute those findings. And so in the end, we end up generating lots of data, lots of papers, lots of grants, lots of studies, but not lots of improvement in how the clinician treats the patient, and how the patient, the prognosis and the outcomes, for that patient. And so that was, kind of, damning, assessment, and really is, rather important, motivator to, how do we try to improve, on this, kind of state of the art back in 2012 or so. So there's lots of reasons, that, these, concerns, are expressed. And we'll talk about them and look at issues of them. But certainly, we're using often low-powered studies. Diagnosis is not a great target. We don't really publish proper and complete methods and results. And publication bias leads to kind of a skewed literature. And we'll look at each of those sort of ramifications as we go through this presentation. So again, while I'm using sort of a prototypical analysis from the neuroimaging domain, hopefully you in radio listening land can warp this into the appropriate stages of your own type of work. But clearly we start with some sort of data acquisition and activities and experiments on subjects, imaging, things like that. Generate a bunch of data, imaging data, behavioral data, apply analyses and workflows in order to generate some derived data and some statistical results, and we go off and publish those. And some of that data and all of that literature, become distributed, in PubMed and other sort of queryable, places. So each of these stages, have different implications about, how we currently do those and how those really can, evolve, to trying to do a better job of, improving our infrastructure for doing reproducible neuroimaging neuroscience. So coming back to one of those key subphrases of that Insel, quote, we have approximate replications of, the findings we tend to find, in a way that neither confirms nor refutes them. So again, that is one of these, driving, types of statements, and, so 3 points, come to mind here. First, that it's impossible to confirm or refute something that you cannot first replicate. So if I see a paper and I want to confirm it or refute it, I better be able to start by being able to replicate it in order to see then, if, different data, different approaches, find that same result. Second, we tend to not publish our findings, with the necessary details in order to support replication. So again, the PDF, the traditional publication, and word counts and readability and sort of the human aspects of things really are not commensurate with the highly digital, highly complex, highly computational nature of the science that we're doing. So by the definition of words, we're really not providing all the necessary details in our general way of disseminating knowledge, the publication. So the third point here is that when it comes to examining either re-execution or the generalizability of an observation or a claim, it turns out that every single decision that we make, every choice, everything we do matters in terms of that output result. So just walk through a couple examples of this, and again, I think it holds in many different contexts, but just to put some examples onto that last statement, exactly what operating system, computer system you're using, can make a difference. In this case, a simple paper that we talk about later in the presentation, takes the exact same software, FSL version 5.09, the exact same data, runs it in a Mac operating system, runs it in an Ubuntu operating system, and documents that the same measures that are coming out of that same software are different as a function of operating system. Now there was ways to ameliorate this, but again, it's important to know that even something as simple as what your operating system is, what your version of software is, what the version of the operating system is, can make differences in what's the same data and the same workflow. Similarly, and clearly not surprisingly, the data, how much data you have matters, in important ways. And a little example I use of this is looking at the sex effect of hippocampus volume in typical subjects. We could go back to the state of the literature back in 2005 or so, where the NIH funded a large study at the time, 325 pediatric population across 7 sites, and this is the so-called NIH pediatric database. You look at that data, large database, look at the sex effect in the hippocampus volume, and you see sort of a 0 effect, but a pretty large error bars. Fast forward to 2011, where the PING, the Pediatric Imaging Neurocognition and Genetics study gets published. So that's sort of 1,200 subjects from 8 more sites with a much more modern imaging acquisition, much more modern segmentation technology, and lo and behold, we now begin to see a sex effect in the hippocampus volume emerge. Now this is not inconsistent with that 2005 in that it falls completely within the confidence limits of those original studies, but we've now tightened the error bars and been able to refine the method, refine the measurements, and get to a data size that begins to let us observe this type of finding. Then if you fast forward further to 2015, more publicly available data becomes available, and then you can see that that effect has begun to sort of stabilize with the new data that's becoming available. So again, data size matters, but not only size, sort of the era and quality of data matters. So just because, and again, I'm one of the folks who pushes very hard for lots and lots of data sharing all along, but again, there is data quality, there is data age effects, and not all data is created equal. But again, to assess that and understand that, it's really better to have that available, and then to make the choice, make the rational decisions about how to use that information as it's shared. The just a somewhat trivial but informative exploration of this number of subjects type of issue. In this case is a simulation, statistical simulation we ran using the PING data. Again, PING is a Pediatric Imaging Neurocognition and Genetics study, ran out of San Diego, Terry Jernigan, Andersdale. It had 12,000 subjects, and so sort of our final little observation over here is sort of the expectation of this about 200 cubic millimeter sex based volumetric difference in males versus females in the volume of hippocampus. But you can easily do the bootstrapping and sort of subsampling exercises. And if you had studies of select only 10 subjects from that, 10 males, 10 females, and redo the analysis and permute that, thousands of times, you get this, kind of distribution, of, effect sizes that you would observe. Pick, 250 sub-subjects, run that permutation. This is the distribution of, effect sizes that you see. So ultimately, all we're doing is, actually, demonstrating, the power, calculation in terms of an effect size, which is about 200, cubic millimeters, and a measure of a certain, variance, the free surfer hippocampus volume measurement in, healthy, children, across the, 5 to 21, age range. And we see that for, an effect of 200 millimeters, you really need to have, a 200 or 250, subject, size, before you begin to clearly, clear that significance, of that effect and that distribution. So again, not rocket science here, but it reminds us that, again, when we're looking at small things, when we're looking at moderately large population variance, we really do need to get into orders of magnitude larger studies than we had been doing, sort of in the old days. And so again, that N, that, tends to be needed for even sort of a moderate to small, effect size, is an important thing to keep in mind, and how that, relates to the types of studies and the subtleties of, cognition and mental health, that we're trying to disentangle relative to larger effects such as sex and age and socioeconomic status and genetic ancestry, et cetera. So the next in line in the everything matters rant is what tool you select, matters. So while on the one hand, we might be looking at the volume of, a cortical region, the left caudal anterior cingulate. In this case, there's at least, there's more, but we're looking at two different tools, one called ANTS and one called FreeSurfer, both of which make a measure of the left anterior cingulate volume. And in this case, we have two versions of FreeSurfer, version 5.1 and 5.3, and we have one version of this ANTS software. So the good news is, FreeSurfer between versions has a very tight, correlation. So they didn't do anything in version 5.3 to muck up, the measurements relative to what they were doing in 5.1. On the other hand, the two FreeSurfer measures relative to the ANTS measures, while statistically significantly correlated, are really correlated at not an exceedingly, high, fidelity. So while statistically correlated, these really are not, exceedingly well representative of the same data. Now, we're fortunate here that this is 800 and some subjects, so we can see this correlation. But again, the one measurement is not really a great proxy for the other measurement, and so therefore a concept such as the volume of the left caudal anterior cingulate, is really rather different, if you're looking at it from the point of view of FreeSurfer versus, ANTS. So therefore, the types of findings and things you might see, could be different. And so I'll use that as a jumping off place to demonstrate, okay, fine, they correlate significantly, but does it matter? Well, the answer is yes, and I'll illustrate that, but I'll also illustrate it in the context of something called Siegel's law. So Siegel's law goes something like a man with a watch knows what time it is. So in this case, if my watch is FreeSurfer, I have one watch. My watch is FreeSurfer 5.3. The time, the analog of time here is I'm measuring, in this case, in the ABIDE, the Autism Brain Image Data Exchange. I'm looking at the effect of the diagnosis of autism or not, based on the volume of a set of 48 different cortical regions. So my one watch is FreeSurfer. The time I'm measuring is how different is the volume of this region in the subject with autism versus subjects without autism, and I find a nice set of regions that have a diagnosis effect and a bunch of regions that don't. And so this is just rank ordered on the effect size, and that's the time, so to speak. The second part of Siegel's law, though, is but a person with two watches is never sure, because in general, two watches are never exactly the same. And so if you have two watches, you don't know which one is right or either right. So having two watches, you don't really know, at all exactly what time it is. And again, the analog in this case is the effect that we saw before, that free surfer and ants. Ants is our second watch. The time we're measuring is the effect of the diagnosis of autism, and we see that our second watch gives us a rather different view of time, of where the differences in the brain volumes are in the subjects with autism versus typical controls. Now, again, my point here is not to argue about which is right or wrong. My argument here is to make sure that we're acutely aware that different tools, even if they're measuring nominally the same thing, have different biases, have different assumptions, and can give different views. And so the observation of differences is really predicated upon the exact tool selection that goes on. And sometimes we forget that, so that's part of the point of making sure that we keep that in mind. And clearly, again, as well, exactly what statistics one uses matters. So in this little simulation, we go back to looking at our fun hippocampus sex effect. We're looking at the ping data, so it's about 1,200 subjects. We have a grand volume as a function of sex is related to age, site, socioeconomic status, total brain volume, and genetic ancestry factor. So those are all the covariates that we could use, and all of these are known to have some effect in the measurements of brain volumes. So we essentially permute, create an ensemble of these models. One model that only has age, one model that only has site, one model that only has SES, and a set of models that have two of these: age and site, age and SES, age and total brain volume, etc. So we create sort of all the different permutations of these models that could exist, and ask what is the sex effect given that ensemble of different models. And so here we're plotting the effect size on the x-axis. So this is an effect size of 600 or so, and this little grouping here has an effect size of about 200 or so. And then the y-axis here is the r-squared, sort of a goodness of fit representation. So what we see when we just plot all 128 of those models, the permutations of this set of factors, is we see these two little clusters. This one cluster has a large effect, and this one cluster has a much smaller effect. And the only difference between these two clusters is when brain volume is included as a covariate. Now that makes complete sense. Sex is related to brain volume itself. So if we discount the brain volume difference between sex, we get left with a radically different representation. So again, this big example, covariating for brain volume makes a huge difference in that. It makes sense. It also varies with sex, so that's fine. But more interestingly, so each of these circles is the effect size estimate, and the whiskers then are the 95% confidence limit on that effect size estimate. And so within here, again, we're seeing a cluster, and many of these models are significant. I.e. their whiskers, don't touch, the zero effect size, but not all of them. So some subset of these models, if that was the model you happen to choose, are going to end up, not being significant, whereas a different subset of those models will end up, being significant. So again, I'm not here to debate exactly what the right model is, but only to use this as an illustration of, again, exactly what model we're using can affect what does or doesn't, end up being portrayed as significant. And also some of these models, are much better at predicting, the overall variance of the data compared to others. So again, when we took out brain volume, we, doubled, our, ability to, accurately, model the data, but we also, dramatically reduced the effect size of sex on the hippocampal volume here. But again, that's closer to reality since we didn't want the total brain volume, interfering with that observation of the sex effect, in the hippocampal volume. So again, lots to worry about in terms of what the right model is, what the right approach to modeling when there's lots of covariates and lots of things that also have significant effects on the observation of interest. So fine, there's a bunch of sources of variance that I've illustrated for you. But that's why we have a big literature. That's why we publish lots of things. These sources of variability will work themselves out in the published literature, right? Well, no. And for a couple reasons, we tend not to publish negative findings. And that has to do with things like publication bias and file drawer effect that we could talk about further later if one wanted to. So that a given published false positive may not see much contraindication to it, because people don't want to publish the fact that no, that region didn't show up. They'll usually go and look for something else that did show up and publish that. So when we see something, when we do see something that's different, it usually gets wished away with statements like, oh, our population of autism subjects is a little bit different, or oh, we used a different method, so it's okay that we're getting different answers. And so now the literature then gets a second answer and a third answer and a fourth answer that are all a little bit different and all implicating sort of different regions, and never coming back and asking itself, why are we not seeing, or are we not seeing some of the common regions across this different set of publications. And again, so a trivial or simple illustration of that is my finding. I look at these two regions, region A and region B. Region A is important and significant. I report that in the literature, yay. You come along with your paper, you don't see anything in region A, but in your case, region B is important. So you publish, region B, is important. So now both of these may be false positives, due to low power or whatever, but our literature doesn't know that. Our literature doesn't know our inconsistency. Our literature just has, region A is important and region B is important, in this disorder, and along we go, merrily. Next person who finds, region B looks through the literature and says, oh yes, so-and-so saw that, I'm consistent with the literature, ignoring, of course, the fact that, someone else, didn't see that. So again, these ability to constructively or destructively sum up, these different findings is really just not happening properly in the literature, as we report it. So, and that builds upon itself, in a literature. And one of my favorite examples, of, kind of a semi-pervasive effect, certainly in the volumetric literature, is documented in this publication here by Anne Lefebvre and Roberto Toro. In this case, they're looking at what was felt to be a pretty stable finding, that across lots of publications in the autism literature, if you look at the corpus callosum volume, you find significant decrease in corpus callosum volume as a function of autism. So again, if you just read the literature, you read lots of articles, you can find lots of articles that support that idea, fine. You can then go off and do a proper meta-analysis of that literature, and that's shown here. There's 14 different publications, and you do the meta-analysis on this effect, and you get a significant effect of the literature, and you say, yep, that's what I expected, that's what I feel like when I read the literature. All is well with the world. The literature is consistent on that, despite some saying the effect is really big and some saying the effect doesn't exist. In general, the literature suggests the effect is about a 0.5 standardized mean difference. So what Roberto Toro's group did was tried to confirm that. So if that was a true fine finding, one would like to be able to see that not just in the retrospective published literature, but in a prospective large data set of data about subject with autism. And so in this case, using the ABIDE, the Autism Brain Image Data Exchange data, they found 694 subjects in the 7 to 40 year old age range. 328 are patients, 304 are control. I'm sorry, 366 are controls. Ran a particular software package, FreeSurfer 5.1, and looked at the corpus callosum effect. Well, the types of things they observed were things that you would expect. There was a significant side effect, and that's been seen. And this came from about probably about 20 sites. So it's a large number of sites to generate this data set, but there was a significant side effect. There was, as expected, a significant age effect. And there was, as expected, a significant sex effect. But unfortunately, they did not confirm, a group effect, a diagnosis effect of this, corpus callosum volume and the diagnosis of autism. So that's, upsetting, and that, something that was so clear, from the traditional published literature that there should be an effect, couldn't be replicated in a prospective mega-analysis as opposed to the retrospective meta-analysis. So it turns out there's a good number of reasons and background to this, and I don't want to dwell too long, but part of the point is power. The biggest of those prior studies was 113 subjects. The biggest power to see an effect of 0.3 standardized effect size was only 36%. So in general, all of those publications that were seeing this effect were woefully underpowered to see that effect. And if there were an effect of that size, there really ought to be many more publications or observations that did not see it. So again, this is an example probably of this publication bias and reporting bias, whereas the mega-analysis that was performed had a 99% power to detect an effect of this sort of 0.3 standard deviations, and yet this is the publication that did not see this. So the scarcity of negative results is a problem, and the woefully underpowered, in retrospect, the woeful underpoweredness of the literature that went into that original meta-analysis, is problematic. So ultimately, what this kind of refers to is not that nothing is going on in the corpus callosum, but the model of that sort of simply diagnosis relates to corpus callosum volume is really too limited a model, and these studies were underpowered to look at sort of the covariate, sort of the whole system of what's going on here. Is that diagnosis is related to brain volume, diagnosis is related to IQ, IQ is also related to brain volume, and so all of these things are co-varying together, and so yes, there is an effect in corpus callosum, but if you control properly for IQ and control properly for brain volume, that effect is not necessarily a direct effect of diagnosis and corpus callosum. So again, by getting to properly sized studies to be able to more efficiently disentangle the types of covariates that are going on, one can change the view of sort of what the causality or what the relationship in that model will be. How are we doing on time? Okay. So fine, lots of things are a problem. I always get yelled at for being a rather pessimistic person, and most of my research associates get very annoyed with me for being so negative. So let's try to turn a little bit more positive here. So steps to recovery. Doing truly reproducible neuroimaging research is hard. There are just so many things that we've seen that you have to do to get it right. So that's where sort of ReproNim has been trying to focus a lot of our efforts in terms of establishing sort of a comprehensive set of tools and practices that are designed to advance the reproducibility of each of these critical stages of the neuroimaging research process. So again, I've sort of alluded to this, but I want to say this even more explicitly is reproduce what? So there's at least two domains of places where we're concerned about reproducibility. I may want to reproduce in the sense of re-execution of a specific result. So for a specific paper, given the same data, given the same approach, can I re-execute that observation? So in this data set, with this tool, can I confirm that the hippocampus is 203 millimeters larger in the boys and in the girls? Great, that's interesting and useful, not very scientifically exciting, but sort of an important foundation point. The slightly more interesting scientific question is reproduce in the sense of generalizing of the claim that when I use different but similar data and a different but similar approach, can I generalize? Can I reproduce the same claim that came from my original observation? So the general claim might be something like hippocampi are larger in boys than in girls, and to generalize that, I'd need additional data to confirm the claim that may have come from my first observation for that to generalize in the literature or across other observations, use additional data, use additional tools that look at volume. And if all of those corroborate, then we can begin to generalize and reproduce the claim that hippocampi indeed are larger in boys than girls. But if there was something about the measurement of hippocampi, or something about how I claim what I meant by boys versus girls, or what the age limits are, or things like that might matter. And so therefore one may have to be carefuler in how they distinguish the groups by which this observation, this claim holds over. And so again, so all sorts of things that just have to be a bit more careful than we tend to be. So fine, a different version of the same thing is this original data, the original paper you write has some data, has some analysis, has some result. We argue that what we're missing, the first thing we're missing, is this concept of reexecutability. And I'm guilty of this, especially because I'm so old and have been doing so many studies for so long, that I probably cannot get to the same data from a study I did and get to that same analysis and verify that I can get the exact same result from a paper 5 years, 10 years, 20 years ago. So we really, I think semi-exemplary of the literature, are not really engaging in science and in the way that we can at least establish this sort of core reexecutability of my original finding. But having that reexecutability in place is really the necessary foundation point for systematically and sort of scientifically exploring the generalization of my claim. So can we muck around with similar analyses on that same data and get a similar result? Does the tool matter? Can I use that exact same analysis and use similar data? My kids with autism compared to your kids with autism. If the finding really is related to autism, it shouldn't matter if it's my set of kids or your set of kids. If it's really about volume, it shouldn't matter if I'm using this tool or that tool, if these are valid tools. So ultimately, we want to get to the generalization statement that similar data and similar analyses should yield that similar result. But we'd like to be able to do that in a systematic way, and not as we kind of right now, we have my paper and we have your paper, which is on similar data and similar analyses, but we can't rationally understand the differences when I don't replicate and we don't know, and which often happens. And this is because we don't really characterize our data and our analysis and our results very well in our current literature. And this idea of similar has lots of wiggle room in how one can use that to their own purposes. Again, if you're trying to write something, if you had two functional MRI experiments and each had a foci of activation close but not quite overlapping. Well, if you wanted to tout the novelty of your approach, you could say, my approach and their approach get completely different spots because they don't overlap. Great. If you had a reason that you wanted to say the similarity of these results, well, those two spots, yeah, they're close, they're part of the same system, I'll say there, and there's anatomic variability. So again, at the behest of the writer, one can often take results and decide if it suits them better to call them similar or dissimilar to their purposes. And again, this happens just because we can't get to the exact answers and the exact methods to both of those types of observations and really use those in a systematic fashion. So the steps to recovery, really, I'll try to illustrate by example here and then work backwards to how we might get there. A traditional publication publishes some traditional correlation analyses. We see a PDF plot. We see a bunch of observations. We see a fit somewhere in the text. They tell us all the details of how the data was analyzed and how the statistic was done and what the magnitude of the effect was, and blah blah blah. Lovely, you read it and you're happy. The ReproNim variant of that really wants to shift, do a sort of a paradigm shift under how we do that same publication in sort of the reproducible, reexecutable fashion. So in a ReproNim version of this, same plot, each point knows, in some canonical sense, all sorts of information about where that point came from, its provenance. Who was the subject, that point is representative of? What was the demographics? What were the clinical variables, et cetera? what MRI scan was used, to generate, that, observation. What was the scanner? What was the acquisition details? And where is that scan living, at the moment? On my hard drive, out in some public repository? What workflow was used, that took, that MRI scan and turned it into this, volume of a corpus callosum measurement? And this is a volume of a corpus callosum measurement. Well, where does that fit into the constellations of measures? What is a volume? What is a corpus callosum? What part of the brain does that belong to? How does it relate to other parts of the brain? So all of those are features of every point that we should be able to generate. And if we just keep the provenance and keep the annotations about that point as we generate it, each point can then sort of recreate itself. That point knows what workflow generated it. That workflow can exist in a container or somewhere that can be re-executed. So given that point, it can be regenerated by anyone who had that container and the ability to execute that. Given that you can get to that data and you can get to that specification, that could be anyone could re-execute that. It also supports then the concept of generalizability. If I take different data, I can do the exact same analysis. If I take that same data and open up that container, I can change the tool, I can change the parameters on that, and so be able to explore the generalization of that point, because all of its history, all of its execution, all of its generation can be captured in a formal way. And in that sense, the point is fair in that some way that point can be housed locally or publicly in a way that's findable, accessible, interoperable, and reusable. And hopefully that will resonate a bit with Marianne Martone's presentation from a while back. So fine, if we can generate points in that way, that would be great. The statistic has the same issue. The statistic has a version, has a an execution, has a container in which it runs. So given that this pile of data, this statistic can be rerun. Given a different pile of data, the exact same statistic can be run. Given a same or different pile of data, one can has the framework to then version control and track and understand differences that one might make in that analysis approach. Great. So that I just set up sort of a wish that what would I have to do to make all of the provenance and all of the metadata for each of my observations and each of the statistics and interpretations of that observation. So what do I have to do to actually accomplish that? And that's hard. So one of the things ReproNim has also tried to do is to stratify the process into individual components, each of which individually are not as hard as the whole thing, and each can be adopted individually, and each contribute to the overall reproducibility of the research effort. So the ReproNim platform is a sort of a virtual path through lots of different components that we try to improve, sort of piece by piece, one's ability to do these things, just because it'd be hard to do everything at once and start a whole new study and do it this way. But if we can get you to do simple things that are a little bit better than what you did in your prior paper, and then through your sequence of learning and doing things a little bit better, we all can sort of improve the background and the underpinnings of the published literature that we generate. So the stages of research that we dwell upon, the sort of 5 steps that we'll refer to. There's studies, design, data collection, data processing, statistical analysis, and the publication. The principles that we try to apply to each of these stages include sort of proper planning, proper version control, use of standards, annotation, and archival. And so in each of the different stages, we at ReproNim and the community as a whole have a number of different tools and resources that are available to assist in sort of promoting sort of the reproducible execution of each of these different stages. So in terms of study design, you might, in the planning stage, you might really encourage pre-registration. Version control really cuts across everything. As you do your study design, that may evolve. Well, we better understand why and when it evolves so that you know what it is you end up doing. And there's annotation that can be done with the neuroimaging data modeling. Similarly, in collection, we want version control taken care of. So there's tools like DataLad. We want standards such as ReproIn and BIDS to be used. We want annotation to really describe what it is we're acquiring, and we want to do that at the time of acquisition because it's easier to do when you're designing and collecting the data than it is to do 5 or 10 years later when you go to publish it and can't remember what SAM3 variable really means. And there's tools for archival, and we don't need to go into the details of this. There's lots of tools and lots of resources that can be applied to sort of each of these different areas. And again, we could talk further about those tools specifically if they are important or interesting to anyone. So again, a second version of seeing the same thing, has to do with sort of these 5 steps that we mentioned, and a set of tools that really support doing them. And again, the point here is that you don't have to do everything correct, most reproducibly to start with. Pick something. Oh, I want to do my data analysis using DataLad. Okay, well, do that, and that's better off than you were before. Oh, I want to use version control for my scripts. Okay, use Git and do that. And each of these singular things are steps to overall improvement of the overall system. So the last concept is fine. We talked conceptually about wanting reexecutability at the paper level. We talked about a bunch of tools that are available for doing elements of that. So where does this bring us? Where do we end up? We end up in this concept of the ReproPub, which is this reexecutable publication. And of the future is slightly, you can do it today, but again, a lot of our efforts are trying to make it more routine, to do these sort of completely reexecutable publications. Now, what do we have to do a new version of a publication that is reexecutable? Well, yes, we need humans to read it and understand it and like, the study you did. So we need our words, but we need to include additional digital, machine readable, supplementary, information. We need to explicitly indicate what data went into the analysis. We need to explicitly define, the exact details of the workflow specification. We need to explicitly and completely define the execution environment, that supported the running of that analysis. And we have to provide that complete set of results, not just the story you tell about it, because that makes a good story, and that's important, but the complete set of results is what's necessary in order to, 1, verify that it's reexecutable, and 2, to support the negative findings and the anti-findings and the mixing and matching of findings across the complete set, as opposed to the garden path story that you tell about the results that make sense to you. So we need sort of a completely reexecutable research publication that requires the complete description, the provenance of the data, workflow, execution, environment, and results. So we've done a couple examples of this. The first one we refer to as simple 1, which was really just 20 subjects from the NITRC, the Neuroimaging Informatics Tools and Resources Clearinghouse, publicly available data, a very simple FSL volume workflow run in a very simple Ubuntu container built with NeuroDocker. And so the data is a data set which is identifiable and machine readable and machine accessible. The workflow and the results are in a GitHub repo that's been archived into a specific DOI through Zenodo. And the execution environment is a particular container that lives at Docker Hub. So anyone could read this paper, get to the data, get to the workflow, get to the environment, and verify that they could generate the same results. And this was done in a very simple situation. So you could, if you wanted to do that and to verify that you get the right answer. So to some extent, one doesn't really want to do that, but one wants to know that they can do that and wants to be able to represent publications in that way. But this was a silly paper. It didn't really do anything scientifically. It just demonstrated the concepts of these pieces and their connectivity in a traditional publication that can still accompany with these accompanying documents achieve this objective. So a more complex example that I'll end on here is trying to do that same thing, but actually do it in a biologically interesting thing. So we searched the literature for IQ in typically developing children, discovered 3 different papers that did some observations of IQ and structural variables. So we need to discover our own data that's appropriate for that. We need to prepare that data in a semantically appropriate way. We need to select a workflow that makes the measurements that we need. We need to execute that workflow. We need to make sure our results are represented in that semantic representation. And then we need to query that and do the statistics that verify or replicate the findings that we developed from the literature. So again, in this case, we can do that with pre-registration of hypotheses that came from the literature. We have a structural workflow that is using NeuroDocker to containerize a FreeSurfer and FSL and ANTS software. And that container and workflow is available. The data sets come from ABIDE-1 and ADHD 200, publicly available, and the statistical analysis and results are published as a Jupyter notebook. So again, we've accomplished the same things of, yes, we can write lovely words about this, but each of those elements, in addition to the human readable words, are associated with machine re-executable elements. And so this is just one of the hypotheses that total brain volume will positively correlate with IQ in both sexes across the complete age range. Here's the data. We found a significant effect here, and the original report had a significant effect here of a very similar sort of magnitude. So cool, we re-executed that. The old report was not re-executable. This one is, and so anyone could take our version of that. Yes, it's nice that it recreated the prior expectation, but ours can now live and be added to or manipulated as one sees fit. So overall, in these 3 papers, there were 9 hypotheses that were generated, and 6 of those we replicated in the ABIDE and ADHD 200 data, but 3 of the findings that were from the literature didn't replicate. And so again, so one can now, yes, that's sad that those didn't replicate. And we can't really, again, they use different data than we did, and we used a slightly different tool than they did. So we know there's differences, but at least from our version of this, one can now expand and explore that in ways that you couldn't if you failed to replicate their observation originally. So final slide. For some reason, this dawned on me that I should end with the wrath of God or the wrath of the NIH, and use this fear factor ending reproducibility. Just do it, or else you won't get funding. We know there are new data policies coming from the NIH that are going into effect, which are much more stringent in terms of data management and data sharing. Even now, progress reports and competing renewals and things like that can be held up or not awarded if you're not doing your data sharing, data acquisition appropriately. You won't get published if you don't work on reproducibility. Many journals are now beginning to enhance their data sharing and software sharing policies. And if you can't get funding and you can't get published, you won't get tenure. That's semi a joke, since most people don't really get tenure these days anyway, but that's okay. But most importantly, John Oliver will laugh at you. There's a whole lovely segment on the This Week with John Oliver, lamenting how badly many scientific studies and how badly the news media deals with scientific studies that are done in irreproducible fashions. And then so ultimately, adopt reproducibility by design. That's much easier than doing reproducibility at the end. And I thank lots of folks from the ReproNim team and the many institutions and the many groups that work with us. And we are available via websites, emails, Twitters, monthly webinar, training materials, YouTube channel, etc. And thank you. And I'm sorry, I talked a little bit longer than I probably should have.
David, thank you very much for that fantastic overview of the importance of reproducibility, what it means for science, and all the effort that you guys have put into not only sharing your ideas, but your code and your tools for so doing. I think it's great. One couple of questions. So I was impressed by looking at some of the meta-analytic summaries that you provided, and you had mentioned publication bias as one of the sources. And I've published in this area a little bit myself, especially in neuroimaging, and so I have a little, my own thoughts about this, but I wanted to pick your brain a little bit about the sources of publication bias in neuroimaging, for example. What are some of the sources of that? And also, would we do better by not just reporting small p-values and saying, oh, look, something was statistically significant, but doing a better job of reporting effect sizes, power estimates, and stressing what is there beyond just a small p-value? Does that make sense?
Yes, that makes sense. And I think there's a lot of impetus to get away from, maybe not abolish, not defund, p-values, but really, downplay p-values and make sure that effect sizes are reported, make sure that power is reported. Because again, to some extent, so much of what we, and again, the two issues with power is there's retrospective power you calculate from your observation, which, if you have found a, spurious false positive, you're going to miscalculate the power anyway. But again, looking at the difference between, prospective power and retrospective power and what that is. And we'll find that an awful lot of the findings we do have are rather significantly underpowered. Doesn't mean they're wrong, but it means, they're positive predictive value. The likelihood of seeing that again in a new study, is not as good as, an observation that came in a better powered, study. So again, I think, there's a lot of movement towards, effect sizes and, observed power and, really grappling with and just embracing or understanding and working with the fact that, things are underpowered and, need this replication. So while I sometimes sound negative about small underpowered studies, not everyone can do 10,000 10-year-olds and follow them for the next 10 years to look at everything you want to do. I can't be against small underpowered studies. What I am against is small underpowered studies that are done in sort of a private closed space that that don't have a chance of being contributed into the bigger literature to become part of a properly powered prospective study. So that I think is the problem is, closed low-powered studies, not the presence of low-powered studies. I think that's a fact. The NIH just won't fund things that are big enough, and to report power, to report effect size, and publication bias. Like, there's so much requirement, to publish, and even if one isn't, actively p-hacking, there's just lots of, I won't say laziness, but lots of things that people do which are not quite as copacetic in the long term, in part just because, again, myself included, didn't really know any better and were quite anxious, to find something, to publish out of this. And I think the pre-registration therefore becomes an important part of that to help avoid some of the publication bias, to help promote the publishing of negative findings. And again, the challenge with negative findings is you have to be properly powered. Again, negative findings don't magically overcome the power issue. You can be equally underpowered for a negative finding as well. So again, all of these things just need to be more transparent, more published, so that they can be put together and built upon and understood with respect to each other more efficiently.
Fantastic. I liked how your final slide there about what are some of the incentives for reproducible science. And there's the carrot and the stick kind of classification, if I will. One of the things I'm curious about, though, is in thinking about how data scientists and people who are involved in computational, the enterprise of the brain as a computational science, what can their role be in helping to support reproducible brain science? Oop, you're muted, my friend.
Yeah, so someone has to do that in every presentation, right?
Yeah, that's right.
And the answer I gave in that first second was spot on. So I'll just again, it takes a village in the sense that we as authors just need to be aware of this. We as grant writers need to be aware of this. We as reviewers of grants, reviewers of publications need to step up our review criteria. We as editors or leaders of publication platforms really need to embrace the rigor side of this. Again, it's not that you can't publish things that are underpowered, et cetera, but we just need to be doing this in a framework that is constructive, as opposed to sort of siloed into individual publications. And I'm not sure if I answered the question you asked, but that was.
Well, it seems that there's so much opportunity for data scientists who are very interested in developing tools that help promote a science of reproducibility within the science of the brain, huge opportunity for that. And so whether it's the development of ontologies or computational tools or frameworks for how publications get reported in 2021, I think there's enormous opportunity.
Yeah.
I think you'd be one of the first people to agree.
Yes, absolutely. And just because we have a handful of tools, I meant to say, and perhaps did say, that to some extent, I don't care how you get your version controlling or how you get your annotation, or how we have some tools for that. It'd be nice if you used ours. As long as you get your data into standards so that others can use it, as long as you report the provenance of what you've done so that others can re-execute it, I don't care how and whose tool, and the opportunity to lower the barrier to doing that is great. And again, it's a lot of an efficiency thing. People, the end user, needs to be able to do these things relatively efficiently. We can't slow publication down to a crawl, or else people will get upset. So we need to be efficient and deliver them the ability to do these things going forward.
David Kennedy, thank you so much for sharing your thoughts on reproducible science. That is a fantastic amount of work. I really appreciate you sharing that with us today. Everyone who joined us, thank you so much. Everybody enjoy your weekend, and we'll look forward to seeing you next week. Thanks again.